In this chapter we first discuss creating, scheduling, and controlling threads. We then move to processes, which are a resource manager for one or more threads, and how the object directory of processes can be used to publish object and synchronize the startup of a system. Finally, we explain memory concepts including memory protection and sharing. Intime supports an object-structured architecture. When an object is created, a RT handle is returned. Further operations on the object require passing the handle, and the handle remains valid until the object is deleted. An RT handle is a 16-bit value, and each handle is unique on the owning intime node. Handle values 0 and 0xFFFF are never used. A process provides an environment for threads and is used to control the resources consumed by threads. A thread performs the work of the system and is the only executable, active, object. Associated with each thread is a processor context. Memory can be allocated and freed dynamically. A mailbox is used for passing information between threads. A message queue passes data messages between threads. A semaphore is used for synchronization. A region is used to implement mutual exclusion. There are other, non-native object types for iWin32, C++, etc. These object types have alternate APIs. A real-time system is separated into components that execute concurrently to perform the work of a system. These independent execution paths are called threads. A thread is usually written as an endless loop. However, a thread can be written to execute any number of times. Each thread has its own stack area that is used for local variables, and for calling functions and passing parameters. Each thread also has its own instruction pointer, stack pointer, and values for the CPU registers. It is called the context of the thread. The operating system keeps track of this information in a data area called a thread descriptor. One processor core can execute one thread at a time. The scheduler is a part of the intime kernel that is responsible for determining which thread to execute. The transition between threads is called a context switch or thread switch and is transparent to the threads. Events cause threads to be scheduled by the intime kernel. An event can be an interrupt, a signal from another thread, a signal from the operating system. While a thread is waiting for an event to occur, the operating system is free to schedule other threads for execution. When a thread is created, it is assigned a priority which indicates its relative importance to other threads within the system. A thread priority is a byte value that can range from 0, best, to 255, least. In a intime for Windows configuration, the Windows thread runs at priority 254. You cannot use priority 255. Intime schedules threads according to their thread priority. If a thread with a better priority than the running thread becomes ready, it will preempt the running thread immediately. The running thread will go to the ready state. Intime is designed according to the asymmetric multiprocessor, AMP, model. With intime, each core or hyperthread is referred to as a hardware thread, a hardware entity which reads and executes instructions. The term thread will refer to software threads if not explicitly stated differently. Every hardware thread will run an individual instance of intime. Intime does not migrate threads between hardware thread, instead threads are locked to the hardware thread they have been created on. Software threads are in one of 5 states. Running, only one thread can be executing at any given time in a hardware thread. This thread is called the running thread. It is always the highest priority thread of the ready list. Asleep, when a thread is waiting for an event to occur, it is in the asleep state. Ready, a thread that has all the resources it requires to run, but is not running, is in the ready state. A thread goes from ready to running when it is the best priority thread in the ready state and it is of a better priority than the running thread. Suspended, a thread that is in the suspended state does not consume any CPU resources. It must be resumed by another thread. Associated with each thread is a suspension depth which has a maximum value of 255. If you try to suspend a thread more than 255 times, you will receive an E_limit exception code. If an attempt is made to resume a thread which has not been suspended, an E_state exception code will be generated. Asleep suspended, a thread that is asleep when it is suspended enters the state when the running thread suspends the sleeping thread. If its event occurs or its sleep time expires before it is resumed, it will enter the suspended state. If it is resumed before it awakens, it will return to the asleep state. The round-robin priority level, RRP, specifies the priority level at end, numerically, above which threads will be time-sliced within a priority level. This value can be changed with the eNtime configuration utility. By default it is 140. Threads running at priorities better than RRP will not be time-sliced. When more than one thread at the best priority is ready, and the priority is not numerically below RRP, each of these threads can execute for RRT milliseconds. Again, this value can be changed with the eNtime configuration utility and by default it is 50 milliseconds. Note that the Windows thread if present runs at priority 254. When there is only one thread ready at the best priority, no round-robin scheduling takes place. Thread priority ranges from 0 to 254, with 0 being the highest priority. The thread start address tells eNtime where to start execution. This is usually specified as the name of the C function that contains the thread. The stack size must be at least 4096 bytes, internally always a multiple of 4K is allocated. The fourth parameter is passed to the newly created thread and can be used to pass any 32-bit value. A typecast is typically required. If this call succeeds, its return value is a thread handle, a 16-bit number that is returned by the operating system to uniquely identify this thread. This value can be used to identify this thread in other calls which may be issued to manipulate this thread. The thread handle indirectly points to a data structure, thread descriptor, that is maintained by eNtime to store information about the thread. If a thread wants to refer to itself, it can use null_handle as the value for the thread handle. If this call fails, it returns bat_handle. Get last RT error may be used to determine the exception code, thread specific. A newly created thread preempts its creator if the new thread has a better priority. The system clock ticks at 10 millisecond intervals, so DW wait time is rounded to be a multiple of this interval. We will see that there is also a faster ticking clock. A thread cannot put another thread to sleep. When an asleep thread awakens, it is put into the ready list according to its priority. Do not use RT sleep as a precision delay. The amount of time the thread is actually asleep depends on when in the clock tick cycle, clock interrupt interval, the call is issued. When it wakes up, it may not run immediately, depending on other threads in the ready list. A thread cannot set its priority better, numerically lower, than allowed by the process that contains the thread. The initial thread is created when the process is created, by the eNtime kernel. Its entry point must be called main. Additional threads may then be created by the initial thread. Usually the initial thread initializes the process, catalogs the process name, creates shared memory objects, creates additional threads, creates the deletion mailbox and then waits for a deletion message. Once such a deletion message is received, the initial thread removes all objects and terminates the process. A thread is not called but created, if it returns, either explicitly with a return statement or implicitly by reaching the end of the function, the thread is deleted just as if delete RT thread was called. When the main thread of a process returns, the whole process is terminated. Reentrancy means that the same code can be executed by different threads. This requires that all variables specific for a thread are either allocated on the stack or dynamically. Global or static data can be used to share information between threads. In such a case, typically some synchronization is needed to avoid race conditions. A real-time thread executes in a different environment from ordinary Windows threads, so it cannot use the Win32 API. Instead, there is a real-time API and the standard C runtime library can be used. Printf, scanf, and the like, these are useful for debugging, but are not recommended for implementing a user interface. The functions require a switch to Windows and only a text interface can be built. Open, read, write, close, etc. These provide non-deterministic access to the Windows file system or to the local file system, for a DRTOS eentime node. File name conventions are as in Windows. The local file system on a DRTOS node is accessed when the file name does not start with, or / node name. Accept, connect, listen, req, etc. on a DRTOS node with a network adapter or a local eentime node where eentime controls its own network adapter. These calls allow the exchange of TCP/IP messages with other nodes, including but not limited to eentime nodes. In general, such network communication is not deterministic. Event logging. In Windows, look for eentime in the application and service logs using the event viewer. In DRTOS, select syslog in the web administration interface or use FTP and open file/config/node. A thread always executes within a process. The process owns resources for all its threads including memory and also owns an object directory. A process is an eentime object that provides the environment in which threads execute. A process places a limit on the resources that can be used by the threads within it. Every eentime object belongs to a process. The design of the application system will determine which threads are grouped together within a process. Threads that have similar functions or lifetimes or that need to share global data are usually placed in the same process. The root process is created when eentime is initialized. All other processes are first-level descendants of the root process or they descend, directly or indirectly, from one of the first-level processes. All processes are created by the eentime kernel. On a local eentime node, a normal eentime process is created as a first-level process. On a DRTOS node, such an eentime process is created as a descendant of the eentime runtime loader. Process attributes are stored in the process descriptor and include memory pool, maximum, numerically lowest, thread priority, object directory, virtual segment size. If you try to load a RT process and eentime has not been started, you get the message: cannot load real-time app files, eentime kernel not loaded or not running. A respective event is logged in Windows event log. A process can be created by using the eentime RT application loader, ldrta.exe, also used by eentime explorer, or by executing NTX or eentime API functions. In all cases, all necessary parameters can be passed. All options can be specified by selecting the advanced option of the GUI, on the ldrta command line, pmin, pmax, vseg, odir, xm mode, or by setting respective values for the parameters in the command line version. When creating a process by starting the RTA file, for example from Windows Explorer, all default values apply. Memory pool equals unlimited, unless specified in the RTA file. Object directory equals 64 entries. Virtual segment size equals 8 MB, unless specified in the RTA file. The maximum thread priority of a newly created process is 129. If your process needs to run threads with better, numerically lower, priority, as commonly required for interrupt handlers, use set RT process max priority to adjust. A Windows application can load a real-time process using NTX create RT process and variations of it. In-time applications use create RT process or create remote RT process. The API has options to synchronize the start and wait on termination of loaded process. Synchronized load requires loaded RT process to cooperate by calling synchronize RT loader when it finished initialization. A timeout specifies maximum time for completing the initialization. Waiting on termination also has a timeout option. The exit code of the terminated process is returned. Real-time shared libraries, RSLS, binary objects, similar to DLL files in Windows, are loaded implicitly with the new RT process, when RTA has been linked to respective RSL library. RSLs also can be loaded dynamically using the load RT library system call. The API for creating a process is pretty similar for Windows and InTime. Process attributes, memory pool min, memory pool max, object directory size, virtual segment size, and the process flags related to XM mode and executable data segment are also found in the advanced options of the loader GUI. The API supports process flags that allow coordinated start, proc_wait_for_init, proc_suspend, of the process including debug options, proc_suspend, that causes the process to start in a halted state. The Windows API always requires the handle for the location where to load the binary, color-coded green. The Windows API also has variants for wide string parameters and an option to load the RTA from a binary resource in the Windows application instead of from a file. This simplifies installation and maintenance of a Windows application that depends on real-time code running in InTime. The Windows app binary does include the InTime binary. To specify a non-local node for the InTime API, use create remote RT process. This call also can notify the creating thread of termination and exit status of the created process by use of wait for RT process. System calls for RT process control fall into three categories. Synchronizing the load/start/termination of the created process. Many applications require a coordinated start and need to know when the loaded process terminates. Use these calls in such situations. Forcing a process to end. The terminated process sends a DSM terminate message to each process allowing it to perform any cleanup activities needed for graceful termination. The call waits wait milliseconds and optionally forces a delete using delete RT process if each process has not reacted. A more rigid method to end the process is to directly call delete RT process. Each process will not get signaled, thus does not get a chance for cleanup. All objects contained in each process get deleted. Delete RT process also will return borrowed resources and reset interrupt levels associated with interrupt threads owned by each process. Exit RT process performs similar activities like delete RT process, but does not clear up any C library resources. Rather use the C library exit call to exit an InTime process. Exit avoids possible memory leaks in the root process by cleaning up C library resources. Get/set process attributes, only for InTime API. The default maximum priority for a threads in a new process is 129. Setting the max priority typically is used when interrupt threads are to execute in this process. Get RT process pool info gets all memory pool attributes including size of initial pool, borrowed memory, and parent process handle. It can be used to diagnose issues with memory fragmentation. When the process memory requirement is clear, create the process with a pool big enough to avoid borrowing/fragmentation. Memory pool attributes are also printed by Intex, one of the tools InTime provides for diagnostics. A memory pool has a minimum and a maximum size. The initial pool for a process is created as a contiguous piece of memory with the specified minimum size. If the maximum size of the pool is larger than the minimum size, memory can be borrowed from the parent up to the maximum size. The borrowed memory need not be contiguous to the initial pool. Borrowed memory is returned to the parent pool when the object is deleted, or when the process that is using the memory is deleted. Memory pools allow control over resource allocation, where necessary guarantees can be given by setting the minimum high enough. Also, the pool principle avoids memory leaks when a process terminates abnormally. Apart from the memory pool, each RT process also has its own virtual space. This space includes all allocated memory, plus mappings for shared and physical memory and guard pages, of size 4K, to protect against running off the end of an area. Prior to Eentime 6, non-XM mode was used. Here a process has a memory space that may have non-zero base segment registers. These register values can affect performance on Intel Atom processors, so XM mode is recommended. Every XM mode process has a complete 4 GB virtual address space, minus a 256 MB space to map system code and data, which uses zero base segment register values. Using XM mode is the default in Eentime 6. However, XM mode processes and legacy processes can be mixed. The individual virtual address space of XM mode processes results in switches between address spaces in the following situations. Every system call, the system has its own address space. Thread switches between threads in a XM process and other processes. Handling interrupts when a XM process is running. The overhead in each case is very small. Synchronize RT loader notifies the loading thread that initialization has finished. Set RT process max priority. This call adjusts the maximum, numerically lowest, priority of the containing process. It does not affect the actual priority of the calling thread or any other thread in the process. Get RT thread handles, returns one handle according to the selection. This underscore thread current threads handle. This underscore process handle of the current process. Root underscore process root process handle. Exit RT process deletes the current process, all its threads, and all objects created by the threads. During deletion, borrowed resources are returned to the process's parent, and all interrupt levels associated with interrupt threads owned by the process get reset. This function is called implicitly when the main thread of a process returns. Note, this call does not clear up any C library resources. It is preferred that the C library exit call be made in order to exit an Eentime process. Exit will void possible memory leaks in the root process. Wait for RT process as well as wait for RT process EX, waits for termination and exit code of the loaded process. The EX version is designed for processes that have been created in state suspended and started by start RT process. There is a number of functions that can be used for getting thread state and CPU usage information. First, enable the collection of accounting information, then you can use the getRT-thread accounting function to obtain accounting data. The other two functions can be useful in logging exceptions. Note, all memory, process, thread functions, including the ones on this slide, are used by the Eentime Explorer, intex.exe/r-intex.rta, to dynamically view the status of a Eentime system. Ad hoc snapshots can be taken with Intex and do not require you to write your own code. A process owns resources for all its threads and also owns an object directory to publish information to other threads throughout the Eentime system. The object directory also is used for synchronization during startup of the process. Object directories are used to share objects between threads, in the same or in different processes. Use of object directories can avoid synchronization problems during initialization. The number of entries in a process's object directory is specified when the process is created. The name under which an object is cataloged can be up to 12 bytes. The name is specified in a C string and is case sensitive. If you try to catalog an object under a name that has already been used in that object directory, an E_context exception code will be returned. A byte-by-byte comparison is done with lookup RT handle. If the name is not found in the object directory, the thread goes to sleep for the specified amount of time. If the name is not cataloged within that time, the thread is woken up with an E_time exception code. To remove an entry from an object directory, use uncatalog RT handle. When an object that has been cataloged is deleted, explicitly or when its process is deleted, the corresponding cataloged entry is not removed. The application model recommended for all InTime applications, and also generated by the wizards, uses the root directory to catalog only handles of processes, and of some objects created by the InTime kernel. Objects created by a process, that should be visible to any process are then cataloged in the directory of that process. This leads to the following lookup sequence for an object named obj created by process named proc. H process equals lookup RT handle, H root, proc, wait underscore forever. H object equals lookup RT handle, H process, obj, wait underscore forever. The same string must be specified in both threads. The two threads can be in the same process, but this function is most useful when they are in separate processes. Use a null underscore RT handle value as the process parameter to specify the process that contains the calling thread. If the system is distributed across several nodes, the same mechanism applies but additional calls are to be made. Memory can be allocated statically, by the loader, such as code and data areas, or dynamically as needed. All real-time memory is in non-paged space. This chapter also introduces functions to share memory between processes. InTime always works with physical memory, and although it uses the processor's paging system for memory protection, does not do any demand paging or swapping of memory to disk. When InTime is started in the InTime for Windows configuration, it allocates physical memory from Windows non-paged pool or from excluded memory. In the InTime distributed RTOS configuration, it owns all memory by default. The memory available to InTime is then issued to real-time processes as needed. The various pages allocated to a given real-time process need not be contiguous, although any one block will always use contiguous memory. This may be relevant for doing DMA. Each real-time process has its own virtual address space, starting at address 0, extending as indicated when loading the process. Different real-time processes may use the same logical addresses, but these will be mapped to different physical memory pages. There is an option to share one or more pages between processes. InTime applications have strong memory protection mechanisms, even in InTime for Windows configuration. This is in stark contrast to competitive solutions which require the real-time threads to be run in Windows kernel mode, without any address isolation or memory protection. Dynamic memory areas, called virtual segments, VSEG, because they are managed by the InTime Virtual Memory Manager transparent to the user, are available to any InTime application. This implementation of memory is called the flat memory model, which is loosely defined as a memory model where the code, data, and stack are all contained in the same segment. The model uses 32-bit pointers to access all memory types. All addresses are guaranteed unique within a process. Let's have a closer look into the layout of a virtual segment. Each real-time process, comprised of one or more threads, is placed in its own segment, with a unique segment descriptor. Thus, each real-time process is isolated from other processes, including the Windows process which occupies its own segment. If code tries to access an address outside of its segment, a general protection fault is generated. Every process is assigned pages of memory for code, data, stack and dynamically allocated memory. By separating the pages with unallocated memory bands, memory overruns can be detected. If an address outside of the allocated pages is accessed, a page fault is generated which is trapped and treated as a memory access violation. Code is protected by being placed in read-only pages. The page size is 4 KB. The original design of the InTime memory system is such that the kernel manages a total of 4 GB of virtual memory for the entire kernel and all of the applications loaded on it. This has become a limitation for some classes of application, so a new feature, called XM, Extended Memory, was introduced in InTime version 6. An XM process, extended memory process, has its own separate 4 GB of virtual memory space and does not use AVSEC allocated from the system virtual memory space. The top 256 MB of the virtual memory range for an XM process is reserved for use by the system, but the remaining 3.75 GB may be used by the process. There are two ways of allocating dynamic memory, each intended for a particular usage. For dynamic memory that will be used within the process only, the page alignment may cause a lot of wasting. In that case, the standard C functions malloc and free, or the C++ features new and delete, along with native intime functions may be a more efficient alternative. If you want to pass memory to a thread in another, RT or Windows, process, you should allocate shareable memory. Such memory is always aligned on 4K boundaries and there are guard pages before and after the area. For such shareable memory a handle can be requested, which can then be passed on to another thread, who maps it into its own address space. Shared memory can be used as very efficient method of IPC, inter-process communication, but then requires careful synchronization of read/write operations of the threads involved. If the goal is to share memory between threads of the same RT process, the C functions malloc and free can provide dynamic memory to a thread, which creates the data area, fills it, and releases the dynamic memory area when no longer in use. This type of memory is aligned on a 16-byte boundary. The pointer to the dynamic memory area can be made global for the process, or can be passed to another thread in the same process via a data mailbox. Although such a pointer could be passed to a thread in another process, it cannot be used in that context. Note that free returns the memory to the C library free space, but not to the process memory pool. Such memory is only available for further mallocs. Use heap_compact to return freed memory blocks to the process memory pool. If a process is deleted, all memory is returned to its parent process and available for other use again. The C library heap functions are implemented with native intime functions for heap management and heap debugging. A heap itself is implemented using mpools. There are various ways of debugging heap memory problems, so as overwriting after free, and memory leaks. One of the sample projects installed with the SDK, deals with that. It is called Memory Heap Debug Sample. C runtime heap functions are implemented with native memory allocating and management functions of intime. The native functions also can be used by applications directly for fine-grained control of the memory in use. Examples are fixed size buffers filled, processed, and reused.